Hey folks, thanks for tuning in. This video we're going to be going through a recent LLM contest on Kaggle, ended a few months ago. If you've never worked with LLMs before, hopefully this video will be a good place to learn a bunch of stuff. If you have worked with LLMs before, this contest was a little bit odd and kind of uncovers some interesting techniques that hopefully will be insightful. As always, there will be chapter descriptions in the links below, so feel free to jump around and let's get started. So this contest is called LLM Prompt Recovery. Basically, the goal of this competition is to recover the LLM prompt that was used to transform a given text. This discussion gives, I think, a better graphical view of what's happening here. So the original text is "I love birds singing." Prompt: rewrite this text in more Shakespearean style. You pass through the model, and this is like, sure, workflow that anybody who's watching this video has done before. The contest, though, is trying to get you to kind of reverse engineer this and guess what the prompt was. So that gives you the data that you'll be tested on, right? They'll give you the original text, they'll give you the rewritten text, and then your model has to figure out what the prompt was that rewrote the text. So the way that this is scored, right, is you have the predicted prompt and you have the true prompt, which is the ground truth. It's going to be passed through the sentence T5 model, which basically just you send the text to the model, it returns tokens. If you're not familiar with the tokenization process, is what basically you need to do to transform text into a numerical representation to pass to a model. So if you've never done tokenization, just use that as the takeaway. It returns a matrix because they're dealing with deep neural networks. Anyway, so passing it to the T5 model returns as a string of tokens, and then it's compared using this evaluation metric called sharpened cosine similarity. Not too important that you understand the nuances of sharpened cosine similarity, but just take it away as like it's not looking for the exact words, it's looking for context and it's looking for meanings. There's a bunch of complaints in this contest about like how this was a little fidgety and should have used another, but just anyway, the takeaway here is it's looking for something that's like close to in text. It's close in vector space to the original text, not the exact words. If you get the exact words, then it's of course perfect. Okay. Right. Oh, interesting thing about this contest is that they don't give you any data. So they just say they posted a couple of these like notebooks. The starter notebook we're going to look through right now, which is basically like they say, we're not giving any data. Go off and generate all of your own data using Gemma or ChatGPT, whatever model you want. And so this notebook, we'll go through this right now, is how to generate your own data. So here we're taking in, this is a data set from Kaggle, right? So it's just 4 messages from Kaggle. And then we're going to, we have a bunch of prompts that we're using to explain this 4 messages like I'm 5, right? Convert this into T-shanty, make this a rhyme, right? And then passing that to Gemma to get responses out of that to train your model. So here's how Gemma gets imported, right? So you have Gemma config, Gemma model, model for Kaggle LLM. So Kaggle LLM is asking a model to predict the next word, which is the typical use case of an LLM. Gemma tokenizer, right? So every LLM requires its own special tokenizer, so we have to use the tokenizer for Gemma. Let's see. So the variant of the model that we're using is 7B, which stands for 7 billion parameters, which is the largest Gemma model. IT stands for instruction tuned, and this is the most typically you're going to be using the instruction tuned model when you're working with an LLM. The other variety of the model is just called is the base model, which doesn't have a bunch of the instructions in there. But it's you can think of this as like being kind of pre-prompt engineered for you to reply with the next word. And quant. So quant. So the main trend, the new trend with LLMs now is to quantize your models. And if you ever worked with like a pandas data frame and you've reduced like the D types from like a float 64 down to an integer or something like that, you can think of quantization of a model, something like that, of where we're taking like these big vectors of a model and we're reducing it. There's a bunch of papers you can absolutely take a deep dive in what quantization does, but the takeaway here is that you get a much smaller model that's way easier to work with, way easier to train and to infer with, and the reduction in accuracy on a number of benchmarks is only reduced by a tiny amount. So for most use cases, like in your own work, you're going to mostly want to be using the quantized model. Machine type CUDA, right? Because we have a GPU. Right. So, and then here, we can skip down here. Basically, we're just loading the model here, right? So we're loading the model with all the weights. Don't really need to worry about this too much. We're going to go through how this is the Gemma default code. We're going to look at this, how to do this with the Hugging Face Transformers library in a minute, which is a little better and likely what you should be doing. Okay, so taking the data, right? So original text, rewrite the prompt, and then going through a loop here, and then right, and then you have a data frame at the end, right, of all of the stuff that's been all of the text that's been rewritten. Kaggle being the wonderful community that it is, there's a number of folks who did this on their own, basically took this notebook and went ahead and rewrote a bunch of data sets with their own prompts, generating prompts using ChatGPT to just go and do the same thing, like kind of generating a bunch of prompts to filter the model, to filter the text through, and then Kaggle being great, just posting stuff up, and that's how people use to train their models. So this is the second notebook that the contest pinned up here. This is what I would say is like the basic way of doing this. So if I was asked to do this for work, this is definitely how I would start. This is all the stuff that the folks who are at the top of the leaderboard did, and kind of actually even in the middle of the leaderboard while the contest was going on, were not things that I would definitely not things that I would have considered. This is like the standard sort of way of doing this. So going through this a little bit. So we're using this is, keep in mind, Kaggle is owned by Google, and Google likes to push their frameworks. The main one that they're pushing these days is called JAX, which is similar to TensorFlow or PyTorch. Does this run faster? I mean, I don't really see JAX used too often outside of stuff that Google posts, but I think it's, anyway. But so take that with a little bit of a grain of salt. But anyway, good notebook. Right, so loading the model, configuring, right, our little config class, which people seem to like. Okay, so here, right, we, so all of these, these data sets that folks have posted, we're just using a bunch of them and just conglomerating them, right? So the original text, the rewritten text, and the rewrite prompt, which is what we're going to get the model to try to guess. So prompt engineering. So before I did this contest, I kind of, like a lot of people, sort of scoffed, I think, at prompt engineering and kind of not really realizing what the extent of doing prompt engineering is, like, what it needs to be to actually get an LLM to do anything reasonably intelligent. But if you just simply pass, like, without having like instructions like written like this, to the model, and you just you don't carefully say stuff to the model, it doesn't produce anything of any value. Keep in mind, like, the way that a casual LLM model, right, works is it's going to try to predict simply what the next word is in that comes next in the sentence. So if you ask it a question, say, what is the average temperature in New York City? It's not necessarily going to answer that. It's going to maybe ask another question. It's maybe going to expand that question and kind of trying to guess like what the next word is, because the next word isn't necessarily the answer there. So telling it that it's now its turn to answer that question is what you need to do. That's just very, very basic prompt engineering, and there's quite a lot more like that's been uncovered in this contest and other stuff and other work out there. But yeah. So so here's like a basic prompt. Below, the original text is passed. Rewrite it, with certain prompt instruction, and carefully analyze, the differences, right? And so here, right. So we, they did a bunch of color formatting. So right. So here's the here's the oh, sorry, this is not it. So this is the we're just doing inferences before fine-tuning. Oh yeah, this is what I was looking for. Sorry. So here, sorry, I'll skipping down a little bit. So all this stuff is just done, using a little bit of prompt engineering, making sure that we have everything tokenized properly, which we talked about before, and then passing it to the model with just doing some basic stuff, and it does it's fine. So right, so the passage has been. So the original text is, former figure skater is 5-time, rewritten text, as a magical potion. So the response is the LLM was, this is based on the information in the original text. This is probably, this is probably a bad prompt, because, you probably don't want to tell the model that that it is a magical potion. Can't expect the test set to be like that. But anyway, the response is, it's fine. It probably is going to score okay. Same thing here, right? We have original text, rewritten text, and then the example here is like it was rewritten as an audit checklist. Of this biography of this person. So fine. I mean, this like, it works okay. It's not going to get anywhere to the top of the leaderboard. Now, the next technique that we're talking about here in this notebook, and has kind of taken the world by storm of LLMs, is called LoRA, which stands for low rank adaptation. You can go through the math here and kind of understand what's happening. Effectively, what it does is it takes a low rank piece of the transformer, mainly the attention part of the transformer, and retunes just that, and just simply fine tunes that, as opposed to taking like a large layer of the transformer or something like that, where if you're familiar with adaptive learning, which was the technique before LoRA came along, I think just maybe like a year and a half ago LoRA came along, it was much less effective and a much heavier compute intensive. Don't worry too much about the math. The main takeaway here is that you can tune your models much better with much less compute, and with much smaller file sizes than you can previously. And LoRA combined with quantization, as we saw in an earlier notebook, is the way to go. So typically, what you'll see in practice is you take one of these huge LLMs, quantize it, so you reduce the file size to begin with, and then you're using LoRA to then retrain it. So it's called quantized LoRA is the technique now. The main don't worry too much about the math. You feel free to. There's, I'm sure, a lot more papers out there that there definitely is a lot more papers out there that you can read and go down that rabbit hole if you want to. But the main takeaway is that if you have a corpus of documents and you want to fine tune your model on them, most probably the best thing to do is use LoRA. Quantized LoRA. Right. So, and it's all baked in now, right? So you have, enable LoRA rank 4, right? And then you get, as it shows here, right? You have trainable, the total params, right? And, we're down from, what is this? Billions, 2 trillion, right? We're down to 1.3 million, right? So vastly reduces it, and you're going to get the vast majority of the accuracy. So as we can see here, it's the prompt is pretty good. I think it's actually like pretty close to the this is the training set that we're looking at, stuff that's been turn this into a proposal for historical audit. So this is like very close to what the actual prompt was used to retrain this stuff. And here we're using this is an example where we're looking at we're looking at something that wasn't actually in the training set, and the model does very well. The model does pretty well with rewriting this. Submission, just basic Kaggle stuff of like putting this into a submission. Don't worry too much about this. But yeah, so yeah, really good. So this is how. So just to review this, if I was doing this for real, at a job, this would be my approach, right? Assemble a bunch of training data. Use this doesn't quantize it, but I would quantize the model, and then I would use LoRA to take the training set and to fine tune the model. That would be the approach that I would take if I was asked to do this like in real life. So now where does this get? This contest kind of gets a little wacky and goes off the rails when people start looking for what they're calling the mean prompt. So the tokens, right? So the text is tokenized, and that tokenization exists in like a multi-dimensional vector space. And so looking for like the middle of like the middle of that vector space proved to be like pretty good way of showing the of what the prompt is going to be. So this guy took a whole bunch of those data sets that we saw, like and flattened it to a 2D map using TSNE. This is if you're familiar with like PCA or UMAP, it's a similar thing. It's a similar dimensionality reducer. TSNE is for graphic. It's designed for graphics. So this is not. So these vectors are, very large and, very complex, and, cannot visualize them because there's too many dimensions. But, flattening them to do 2D gives you kind of a good idea of what we're looking at. So it's interesting to see, and he color coded it by the data sets that he got it from. It's interesting to see like the groupings of these data sets way out here. So it's like, so if we go transform the narrative, and this should be pretty close to it, right? Reframe the text, right? So reframe, transform, right? Similar, right? reconstruct the text, right? So it's all kind of, and over here hopefully it should be pretty different. Rewrite the message as a symphony. Rewrite the message as a jazz festival, right? So you can see, like, this is, it's interesting to see, like, kind of how everything sort of maps out. So the as he mentions, it's like some are clustered, and we don't know some are clustered in one area of the embedding space. We don't know the competition space because we don't have the data. So the mean prompts, so looking at the so if you just simply use this prompt like over and over again, it scores like relatively well on the public leaderboard. It's interesting to kind of like sort of, and here he actually has it written in a loop to have the LLM like score it and like kind of get feedback and like figure out getting closer and closer to the mean of where the prompts are. But even weirder than that was, so this is dealing with text, right? So this is kind of like what everybody in the competition was looking at, is like sort of, how to do this textually. But the first and second place, actually the first place guy is great, but his write-up I thought was a little bit lacking. But the first and second place guys didn't even use text. Like they just simply as he mentioned, he brute forces the optimization, meaning that he just looked at all of the 30,000 tokens, just like the numerical value of the tokens, and just brute forced his way through, try to brute force the most optimal mean prompt for the average target vectors, right? So just like not dealing with the words at all, just simply going to like looking at the list of all 32,000 tokens, and just simply taking like those vectors and finding the average of them. But just really, really, really interesting approach. But as he mentions, though, there's a bunch of weirdness happening with special tokens. So there's a bunch of stop word ending phrase tokens that are in the that are in some of these models that you make, and they're not in the T5 token. It's not that important. But the weird thing that they found is that this nonsense word, lurikia, or whatever, I don't even think you can pronounce it, but that's close in vector space to this token, and because of that, that was extremely. It had a huge boost on the model. So it's just like this weird quirk of this of the special token not being part of some things, being part of others, where you had to kind of figure out where these top competitors figure that out, and hack through the vector space and found this nonsense word. Other people in the contest found that too, and figured out how to work with it. So this guy posted a notebook which goes through using that. Oh, this notebook is actually really good to walk through to show how to set this up. So this is using the not using the Gemma models as before with the other notebooks, but it's actually importing Gemma through transformers in PyTorch. So the basic way of loading this, right? We'll get to these libraries in a second. So Torch is PyTorch. Transformers is the Hugging Face library. Hugging Face has all these really great libraries within it. So all the auto stuff in Hugging Face is awesome. And what it does is, so instead of like this notebook, right, where you're loading Gemma right, where you're loading Gemma with, by the way that Google provides, like you go Gemma, you're right, so you have to say Gemma model tokenizer. The way that you load it in here, right, is you say auto model, auto tokenizer, and then you say your model path is, Gemma transformers, blah, blah, blah. And then Hugging Face, this Hugging Face library is smart enough to just simply know that, just looking at this file path, we're loading a Gemma model, a 7 billion instruction tune model. The advantage here is that you can just easily swap out a Gemma with a Mixtral or whatever other model that you want to use within your code, and just the transformers library just simply knows how to configure that without changing any of your code, and it's really makes it really, really powerful, especially now, since this contest ended, and between then and me recording this video, Google has released Gemma version 2. So if you wanted to rerun this particular notebook with Gemma version 2, you would just simply swap out the model path for Gemma version 2, and it would just work, presumably. I assume Hugging Face did this already, but at any rate, so model, auto model for Kaggle LLM from pre-trained. That's the Hugging Face method. Model path, right? We have Gemma loaded up in the model path in that variable. And quantization, and the quantization config, we'll get to that in a second. Tokenizer, right, is auto tokenizer, right? Just again, Hugging Face awesomeness here of just like knowing what stuff's happening. All right, so then let's get to these libraries now. So transformers, this is a little bit redundant from loading this in there, whatever, it's fine. Accelerate and Optimum. Don't worry too much about this. These are tightly integrated with Hugging Face. It works really well with clusters. So if you're working on AWS or something like that, and you have a big cluster of GPUs or CPUs that you're working with, it knows how to work with that. It knows how to optimize them for inference and training. On Kaggle, I don't know if it actually makes a difference because you only have one GPU available. So don't quote me on that. Not sure about that. Anyway, Bits and Bytes. This is also heavily integrated with Hugging Face. This is quantization parameters. So if you look here, right, so we have Bits and Bytes config, right? And so it has like all the other, it has like a whole bunch of other configuration items within it, not just this, but just you get to choose a bunch of your config stuff. Basically, we're saying we want it to be 4-bit config. You can choose 8-bit. I think you can choose 8-bit config as well. I would not, in the quantization type is NF4. Don't worry too much about any of this stuff. If you want to, again, jump down a rabbit hole of like figuring out different quantization options, this is easy enough to go and read about that. But this is like good basic settings. Thing that's like worth mentioning is the BF float. This is like a new data type that's used for quantization. It's cool. But again, don't worry too much about it. You can read for ages about the difference between that and float 16. But just take this as this is a very good basic setup. If you want to do any more, go ahead. Right, so that's how we load up the model. So model path, and then we have the quantization with the quantization config. So we're telling this basically that we, just like with these few lines of code, like with this, variable that that we want to load this model up. We want it to be quantized, and Hugging Face kind of knows the rest. Like within this like little bit of code, it like knows how to set this up. Right. So, right, basic stuff here, right? Pandas, pathlib, right, just basic stuff here of like loading up the data, right? Okay, right, and then getting down here, this is interesting. So the competition metric was a little bit fidgety for folks. So you see people using something called perplexity a lot. Don't worry. Perplexity is essentially looking at like the next word of what is between the ground truth and the output of the model, and it looks at all of the tokens that a model has, and has the model rank each token and determines the likelihood of the token. Don't worry too much about that. It's another way of just kind of getting at, like, is the model getting close to what we're looking for. It's a little less fidgety, so that's why folks wanted to use it. But this is this is part of PyTorch. Where is the part? The cross entropy loss is part of PyTorch. And anyway, the reason why we have it here is so that you can loop on it, right? So you have it as like what I would call your cross validation. It's not exactly cross validation, but your internal sort of validation. Right. So the prompt is organized like this, right? So we have the prompt, the row, right? We're selecting the row from the data frame, and then the rewritten text. Say this to me. Right, and then you'll notice here, right? So just playing around with that like weird nonsense word that is close to like the end the ending special key, right? Is makes the score go up for whatever reasons. And it's just interesting to see like the techniques that somebody found that like by optimizing through the vector space to figure out what the most optimal what the mean prompts were. So all right, so moving forward. All right, so this is the loop that they're going through to rewrite the prompts and make and take this out and to make the predictions. So importing the torch, no gradient. That means just simply we're not going to adjust the gradient. This is how you import a model for inference. So samples append. We're just rewriting the prompt with the row from the data frame and with the prompt. So tokenizing. So tokenizing the samples, returning it as tensors. So this is the inputs. And then the output, we're outputting logits. So this is the reason why we're outputting logits. Logits is the tokens without being put through a softmax function. Softmax is like, this is the raw tokens that are coming out of the model. Don't worry too much about this, but this is the reason this is done here is to because it's needed to be passed to the perplexity evaluation that we had previously, the class that we set up in the code above. Okay, and then down here, and then we're getting perplexity, and then we're getting the predictions. So it's like this. Basically, the takeaway here is we have a loop that we're going through, and we're calculating perplexity, and that's how it works. Okay, moving along to these to the second place finisher. So the interesting thing here is so he has like this prompt that he wound up with, which is just like fascinating. So like this nonsense word, the sentence, so for example, like it's going to be so for the sample example in the one sample that Kaggle gave you was rephrase this text by turning it into a she shanty. So so the way that he would the final prediction would be rephrase the text by turning into shanty, 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 nonsense words, sentence. Like it's just crazy. Like this is the result of finding the most optimal tokenization within the vector space. Just a really odd thing that. Just a really odd bit of optimization and figuring this out. But I think pretty interesting. Okay. Anyway, hope that was interesting and useful. Just to review, this is LoRA was probably the main, hopefully the main takeaway for you. The weirdness of this particular task kind of, I guess, uncovered more of the weirdness of LLMs, which hopefully is something that's also maybe interesting to some folks who had some more skills. Anyway, thanks for watching if you're watching until now, and see you around.